All right, so welcome to Math150 Multivariable Calculus. You should hopefully have already received an email from me. If you did not, that means you are not on the class list. That doesn't mean you're not in the class. It just means that at the point in which I migrated things over from Glow, you were not yet added, probably. Or maybe there is a mistake and Williams does not yet recognize that you're in the class. So if you haven't gotten an email from me, please shoot me an email at sjm1@williams.edu. For the most part, I don't use Glow. I just maintain my old HTML code. It looks like something from the late 90s, but this way, whenever the college updates whatever system they're using, I don't have to worry about updating. The information is all there. There's plenty of material from previous years. So I am teaching this class differently than I've done so in the past. Out of curiosity, how many of you are freshmen? Okay. How many of you still remember high school? Okay. So in high school, you get to meet 5 days a week to cover material. And you have a lot more than 12 or 13 weeks for a semester. We have 3 meetings a week to do more material. So one of the things that you lose when you get to college, unfortunately, is doing a lot of examples, is going slowly through the material, is seeing the applications. This is terrible. Of all the classes I've taught at Williams, the one I hate the most in terms of the time crunch is multivariable calculus. The only way you can cover all the material you need is to move at warp speed. So for instance, how many of you are potential econ people? Okay, you will want to see Lagrange multipliers and optimization problems like that. How many of you are potentially physics? So you'll want to see stuff about Green's theorem, Gauss theorem, Stokes theorem. You know, I can go on and on and on. How many of you are art history? We will actually be going to WICMA to incorporate some of their artwork in terms of multivariable calculus. So there's a lot of different things to cover. It is extremely hard to do it in the regular semester with the standard way of teaching. So I'm going to do this class very differently after today's lecture. This will be a flipped course. The only way this will work effectively for you is if you do the work beforehand. So this means you will watch the video from the 2014 rendition. It is a much better recording than what you will see from this. It was a high-quality camera with a student paid to zoom in. Okay? You will read the book before class. And there will be a Google sheet where if you have any questions, I didn't understand this theorem, I didn't understand this application, I'd like to see a problem on this. Put a comment there for me to know that that's explicitly what you want to see in class. So you can put it there, you can bring it to class, and then we will use the class time productively. So for instance, if everybody is fine with a standard definition, I'm not going to spend time on that standard definition. I'm going to free up more time to do problems similar to the homework, similar to exams, similar to applications. If you do this, you are allowed 3 days where just shit happens and you didn't get the work done. Just email me that this was one of those 3 days. It's different than I have a meet coming up, I have a big play coming up, I'm busy. That's fine. If anything comes up, just give me at least 24 hours notice. That doesn't count. You have 3 days where something happens and you just don't get to it. As long as for all the other days you come to class prepared and have watched stuff beforehand, 60% of your grade will be class participation. And I will give everyone a 92.5 for class participation. To pass the class, you still need to pass the final, but I will give you a huge component of your grade. So this is unusual. Normally you do not have this high of a class participation grade. I will rescale everything else otherwise. Why am I doing this? How many of you plan to spend the rest of your life taking academic classes? Okay, so no one is planning on spending the rest of their days taking classes. So at some point you're going to want to do stuff with the material. You're going to want to either go off to grad school, get an advanced degree, and then do stuff with that, or go directly to the real world and do stuff with that. The most important skill you can get is learning how to learn. I just spent a long time talking to a company yesterday about one of my Williams students. And I had to say, they don't have the same training as the CS majors you're going to get from MIT. The CS major will know far more about coding than this student. But this student knows how to learn, the student knows how to present, the student has the ability to pick up material quickly, and I've seen her do this multiple times. And if it's like other students in the past, for the first 6 months, she will not do as well as the other people, and then within a year, she'll be one of your top performers. If you can learn how to pick up material, if you can learn how to read a book, if you can learn how to watch a lecture, you will have a skill that will serve you in almost anything. Most classes at Williams, you might have noticed towards the end of the semester, they realize a little bit that we haven't quite covered all the material we need to and they have to accelerate. I try to go in the opposite extreme. I try to make the beginning of your semester painful so that at the end of the semester we can go a little bit slower and relax, so when the other classes are kicking in, you've already done the hard work here. I strongly urge you to be at least 1 or 2 lectures ahead in terms of viewing and in terms of reading. This way, if something happens, you have a buffer. And unfortunately, it is quite likely that something will happen to someone here or to one of your friends, and all of a sudden you will need to spend a lot more time on things you weren't expecting. When I was in college, one of my suitemates tried to kill himself. And this was a little bit before the end of the semester. And all of a sudden, my semester was very different in terms of what time I have. So if you can get into the habit of putting material in the bank, you will be in great shape for all your courses. For next year, if you know what you're going to take out the books in the summer and just read the first chapter or 2. Okay, so the rest of the stuff, I'm not going to go through the standard mechanics. It's on the handout. There will be 1 or 2 midterms. I think the lowest midterm will be dropped unless you tell me otherwise. I can't imagine why you wouldn't want the lowest midterm dropped, but I will give you the option of not dropping your lowest midterm. There will be a final. The final will be, I think, like a 2.5 hour in-class closed book exam. Parts of the exams I might allow you to do at home, just on the honor system. Any other mechanics questions? Yes?
You had a note in the email about take-home quizzes.
So there will, I think, be on the order of 1 quiz a week, which you can take home and you do on the honor system. Again, I don't like to use 10 minutes of class time for quizzes. We have so little time already. What I will do is I will give you the option of, if you want to do the quizzes, if it helps your average at the end of the semester, I will have the quizzes count for 5% and then just adjust everything else accordingly. So this would be from the 40% that's left over if you do the 60% option, which I strongly encourage you to do. If you want to do a project, I will also allow you to do a project for 5% of your course. Great. And the point of this is you want to control your education. If there's something that you like that excites you, this is your chance to explore it further. I am deliberately wearing this shirt because a couple of years ago when I was a newly minted PhD, I got an email one day that began, "Greetings, my name is David Kelly. I'm a senior criminal investigator for the Internal Revenue Service." And at that point I just put my head on my desk down and they caught me. I thought and so it took me 5 minutes before I was able to read the next line of the email, which was, "I just read with interest your recent paper in Acta Arithmetica." And I was such a newly minted PhD that the fact that anybody would be reading anything I had done, let alone somebody from the Internal Revenue Service, was surprising. And so it turns out that some of the math that I do has applications to detecting tax fraud. And I've actually worked with students on projects for the IRS, and I've actually given presentations at the Boston headquarters of the IRS. What I want to try to do in this class is I want to show you how mathematics can be used for a variety of problems. So out of curiosity, how many of you are potential math majors? Okay, we'll work on that as the semester continues, but it's okay if you don't major in math. How many of you are potential stats majors? Okay. How many of you are potential science majors? Okay. And then I realize some people could have hands going up multiple times. How many of you are potential humanities majors? How many of you just wish you could have raised your hand by some point? Okay. I just heard a phone beep, so this is a good time for the cell phone policy. So if you are expecting an important call, let me know, and then you don't have to put it on silent. Otherwise, please put it on silent. What I will do is if a cell phone goes off the first time, I will warn the class. The second time, I will flip a coin, and if it's heads, everybody gets a pop quiz. So this will be collective enforcement. Or you can do the Dunkin' Donuts policy, where whoever's cell phone goes off has to provide munchkins and snack food to everybody in the class. So I will allow the class to elect, at the time, if we have to elect one of these. My cell phone is 617-835-3982. It's on that. You're welcome to try to have your friends call me during class. So if I forget to put my phone on, you are welcome to try to do that. I'm usually very good at responding to emails. So if you have questions, shoot me an email. If I'm in my office, it's usually office hours. I'm a little bit different than most Williams professors. I don't want to try to get to know you. So let me explain what I mean by that. I want you to force me to get to know you. And the reason is when you leave Williams, Williams is a special place. This is one of the advantages of being at a liberal arts college. You have incredible access to each other, to faculty, to staff. When you go off into the real world, it's much harder. A lot of times you will be insulated from your boss. You want to make sure they know what you're doing. You want to make sure they get to know you. So I strongly encourage you, come by my office. Shoot me an email. Happy to just chat, take a walk. The weather's getting a little bit nicer. Grab a coffee, grab a meal. Let me get to know you. If you can have 50% success rate in getting your professors to know you, by the time you're a senior, you'll have at least 3 people who can write strong letters of recommendation for you or who will be aware of job opportunities. So I have enormous numbers of consulting opportunities with salaries ranging from on the order of $20 to on the order of $60 an hour for students with basic math and programming skills. So if you're interested in stuff like this, even as a freshman, I've already got opportunities for during the academic year as well as the summer. And the point of this is to give you a sense of what you can do. You already know enough to be useful. Later in the semester, we'll be doing one of my favorite applications of multivariable calculus, the method of least squares or linear regression. Out of curiosity, how many of you have seen statistics and regression? So this is a phenomenal application. So I am actually an elected official in the Commonwealth of Massachusetts. I serve on 2 regional school committees. And Williamstown and Lanesboro recently decided to fully regionalize our schools. And there was a huge stumbling block that if we used the standard state formula, it would cost Williamstown $360,000 for the same level of service, and Lanesboro would gain $480,000. It doesn't seem like this is a reasonable deal. The problem is it's complicated. The state would not tell us what the formula was. But by using linear regression, I could sniff out what the formula was and come up with, within $10,000 out of $3.5 million, how the money should be allocated. So I want to try to show you stuff like this, applications of multivariable calculus. Right? One of the hardest parts of this subject is visualizing things. I strongly encourage you to learn how to use some kind of software. Mathematica is a great example. If you like other things, by all means, feel free to do that. But Mathematica has really good visualization capabilities. If you don't have it on your computer, if you can't access it at Williams, you can go to wolframalpha.com and you can just access it online. It's fine to be able to use this to plot things, or to take derivatives, or to take integrals. You want to be able to do a lot of these things on your own. You want to have some rough sense of what the answer looks like. But it's very hard to figure out what a lot of these things look like. It is possible to give you problems such as, I have a cylinder and I have another cylinder intersecting at a right angle with the same radii. What is the volume of the region in between? For those of you who love problems like this, I hate to break it to you, but I don't love problems like that. So we will, for the most part, stay away from problems such as that. When I was a graduate student teaching multi at Princeton, I asked the students one year if they liked these problems, and they said, hell no. And I said, okay, should we remove them from the curriculum next year? They go, no, no, no. We had to suffer through them. We want the next group to suffer through them. And I just smiled and I said, do you know how many years in a row I've now had this conversation? No class would be the first one to stop it. Okay? There's plenty of busy work problems I can give you. Some of them I will give you because you just need to develop the skill. You need to become proficient at doing the calculations. But I want to really leave us time to focus on why you're taking this. Right? The goal is to learn multivariable calculus. So this is the first lecture. What I want to do today is give you a little bit of a sense of what's out there. And then I'm going to review some of the basic material that you should have already seen, but you may not have seen a proof. So it's always a difficult question as to how much detail do you want to get into. One of the reasons I love mathematics is because you don't say, well, I outrank you, and I say it's true, so you have to listen to me. If I can't prove to you that it follows from a standard set of axioms and assumptions, I'm not doing my job. Now, there are some times when I might need to use a big advanced result from real analysis. And so what I'll say is, in real analysis, you'll then learn the following fact, which is what we need to complete the proof. And I'll try to give you a sense of why it's true and try to motivate you as to why you might want to take real analysis. Is that there are a lot of things that seem true, that seem reasonable, that turn out to be false. How many people here are from Boston? All right, so I have a little bit of an accent at times. If you have trouble hearing me, I will not be insulted. So I want to just start with Russell's paradox. So how many of you have heard of Russell's paradox? Okay, excellent. So consider the set R, which is the collection of all objects in the universe X, such that, and so the colon means such that, X is an element of X. Most things are not elements of themselves. Okay? If you take the list of Super Bowl champions, somebody give me elements of the set of Super Bowl champions. Patriots. And then if you want to make it a multi-set, you could actually say Patriots multiple times. Right? So Patriots would be in that set. Who else would be in this set? Broncos. Vikings. Vikings, okay. I think so. Cowboys, Steelers, not the Eagles yet. Is the set of Super Bowl champions an element of the set of Super Bowl champions? Its elements are teams, not the set itself. Most things are not elements of themselves. If you look at the positive integers 1, 2, 3, 4, 5. Is the set of positive integers a positive integer? No. You're hard-pressed to find something that's an element of itself. Okay? So I'm going to just take all things that are elements of, all x such that x is not an element of x. Sorry. I'm going to take all things that are not elements of themselves, and I'm going to call that a set, and I'm going to call it R for Russell. So Russell came up with this when he was very young, and he sent this to Frege, who was writing up a big monumental work putting set theory on firm, solid foundations. There's a natural question you could ask about this object R. What might you want to ask about it? And if you've seen Russell's paradox, you're not allowed to play right now. So what question would you like to ask about R? So R is the set of all things that aren't elements of itself. So what's the natural thing you might want to know about R?
Is there an exception?
So is R empty or not empty? What else might you want to know? We're talking about all things that are not elements of R. So is R, any thoughts? So we're trying to think of what might be elements of R. Maybe is R an element of R? Is R an element of R? What are the possibilities? What are the possibilities? Yes and no. All right, let's do yes. If R is in R, R is the collection of all things that are not in R. So if R is in R, that implies R is not in R. So there's no need to even do the no case. It's got to be no. Well, it's not even 9:20 right now. We've got plenty of time. Let's look at the no case. So if R is not in R, R is the collection of all things that are not elements of itself. Therefore, this implies R is in R. So you get the absurdity that R is in R if and only if it's not in itself. So what does this mean? It means that our notion of creating sets was too carefree. You cannot just take a collection of objects that have a desired property and say that collection is a set. This means mathematics needs to be dealt with very carefully to put things on firm foundations. I am assuming most of you do not want me to spend time proving that 1/2 is not an integer. There's always the question of how far down do you want to go in the ladder of mathematics. I want to show you something like this to just give you a sense that you need to be careful, that things that seem reasonable could actually be false. And this is why in this class we will do some proofs. And one of the advantages of having you watch some of the videos and read the book at home is this frees up more class time. And if you want to see more details, if you want to get a better sense of why something is true, we'll have time for that. Sometimes when I prove things, I will prove things with additional assumptions just to make the proof easier. How many of you have seen a proof of the fundamental theorem of calculus? Okay, how many of you could reproduce the proof of the fundamental theorem of calculus? Okay, so I will give you a proof, but I will put in an additional assumption that you don't need if you take real analysis. But it makes the proof a lot easier. And it's an assumption that's met by all the functions we study. So as a professor, you have choices as to what you want to do. I would much rather do a simpler proof that's illuminating and easy to follow that handles the cases we're going to look at. Okay, so this is just one of the examples of why we need to be so careful about proofs. So everybody remembers differentiation. Okay, so what I want to do is I want to teach you half of multivariable calculus in less than a minute. Does anybody have a stopwatch? All right, ready? So I like 80s movies. Differentiation. Anybody see the movie Three Amigos? All right. My cultural references will not be good. My kids are 10 and 8. They're a few years away from being old enough so that the cultural references I get from them will work with you. Unless you guys watch like Nick's The Loud House. Does that work for you? No. Yeah. So I'm still a few years away. All right. Three Amigos was a very funny movie. There was a great scene where they were about to have somebody was going to show how fast of a draw he was, and he was asking, does anybody have a stopwatch? Preferably one with a seconds hand. All right. You ready to learn partial differentiation? All right. If f is a function of two variables, then df dx is the derivative with respect to x and taken by holding y constant and differentiating with respect to x. All right. I'm assuming that was less than a minute. All right. That's half the course. Then you need to justify and prove various rules. Let's say I give you the function f of x equals 3x squared plus 7x. What's f prime of x? Yes?
6x plus 7?
6x plus 7. If I give you f of xy is x squared y plus y to the fourth x. I just want to view y as constant. So the symbol partial f, it's read partial f, partial x. This is very similar to the old df dx. Is just take the derivative of this and just consider y a constant. So if I consider y a constant, what's the derivative of x squared with respect x squared y with respect to x? 2xy. And then what would be the derivative of y to the fourth x, considering y is a constant with respect to x? Y to the fourth. So that's partial differentiation. So the technique of partial differentiation isn't that bad. You just hold all the other variables constant but the one you have. Then there's a lot of questions you can ask. What if I take the partial with respect to x and then the partial with respect to y? Is that the same as taking the partial with respect to y and then the partial with respect to x? Does order matter? And so, I didn't bring the right Rubik's Cube. I'm a big fan of Rubik's Cubes. How many of you know Rubik's Cubes? If people want to, I'm happy to teach. There's ways to solve Rubik's Cubes where you won't necessarily notice that things are correct or that things are incorrect if the cubes have the same color on each side and there's no picture. The center tiles could be somewhat rotated. I'll fix it for the 10 o'clock lecture. I'll grab the right cube. So when you look at it, you won't necessarily notice that something has been switched, that there is an order that matters. The Rubik's Cube is an object where the order in which you do moves is highly important. That's painful. It's much easier if you don't have to worry about the order in which you do things. Most things in life, order matters. Would you rather have money added to your bank account and then interest credited, or interest credited and then money added to your bank account? You'd rather have the money added first. So when can we switch orders of differentiation? That's going to be a big part of the class. If I know the derivative with respect to x exists and the derivative with respect to y exists, does that mean the function is differentiable as a function of two variables? Sadly, no. And so things can be very strange. Now, most of the time, yes. And if the derivatives are additionally continuous, then the function will be differentiable. But we'll have to define what does it mean to be differentiable. So in Calc 1, one of the big things you should have learned is the tangent line approximation. Right? If you have a function, then locally near a point it looks like a straight line. Have you seen this? So, here's my function, here's a point, and near that point, it's pretty well approximated by a tangent line. What this means is you can replace a complicated function with a linear function. How many of you have seen Newton's method? Okay, so we'll probably cover that later. It's one of my favorite bits of mathematics. You can use this linear approximation to try to find where the function vanishes. The idea is a straight line is very easy to understand. A general curve is not. We want to replace a function with a straight line, at least locally. And that's the key idea in calculus. It's local. If you want to understand, say, you're driving from Boston to DC. If you look at a small amount of time, your car is really not changing speed that much. And if you know your instantaneous speed, you basically know where you'll be a split second later and where you were a split second before. You can do really good approximations. If you want to know where you'll be in 2 hours, completely different. There could be traffic, there could be construction. You might be making a pit stop. Locally, things will be good, but as you go further and further away, you have less and less confidence. How close are you? So we'll look at approximating complicated functions with simpler functions, and we'll look at the multi-dimensional analog of this. Okay. I want to switch now to the Pythagorean theorem. So this is something you should have all seen many times before coming here. How many of you can give a proof of the Pythagorean theorem? Excellent. How many of you know the only US president credited with a proof of the Pythagorean theorem? Only one US president, yes. Garfield. And who is Garfield? Well, who was Garfield? Williams alum. How did he die? Assassinated. When? Yeah, he's coming back for his 25th reunion. So, just you. Very few of our famous alums get assassinated coming back for their 25th reunion, but just wanted to alert you in case no one else has given you the heads up. You can argue as to whether or not he should be credited with the proof of the Pythagorean theorem. His proof looks strikingly similar to some others. He uses a trapezoid where somebody uses a complete square, but let's prove Pythagoras. So if I have a triangle A, B, and C, A squared plus B squared is C squared. There are hundreds of proofs. You might have seen some of the old proofs where you draw squares coming from all of them, and you have all these strange colored sides and whatnot. Sometimes I actually give a talk on generalizing the Pythagorean theorem and showing some of these proofs. I don't really like those. I'm going to show you two proofs. The first is a nice geometry proof, and the second is a phenomenal one that gives you some insight as to why it might be true, and gives you an insight as to how you might try to guess formulas in other settings. So I'm hoping you're going to start to realize I'm much more about trying to get general skills than specific facts. You're not going to get jobs, you're not going to make headway in the world for the most part with specific facts. This is the era of Google and Wikipedia. You can look things up. You need to be able to connect them. So here's one of the proofs. So let's see. So this is A, this is B, this is B over here, this is A over here, this is B over here, this is A over here, this is B over here, this is A over here. In an ideal world, I would have good artistic skills. I would be able to instinctively measure things well. It's going to be approximately right. So I will have 4 copies of my triangle. Should the area of the triangle change if I just translate it? Should it change if I just rotate it? There is something called the Banach-Tarski paradox, which says you can take a solid sphere, chop it up into 5 pieces, take 3 of the pieces and translate and rotate them, and you'll get a complete copy of the sphere with nothing missing. And take the other 2, translate and rotate them, and you'll also get another copy of the sphere. As an application, take a solid ball of gold or a stack of $100 bills, and you can double it. So why am I not doing this? It needs to use an assumption called the axiom of choice, and the cuts are so bad they cannot even be described. So if you don't believe in the axiom of choice, you actually can't do the construction. If you believe in the axiom of choice, you can. And this is just another way of just trying to alert you to the fact that we've got to be very careful in mathematics. When are we making assumptions? I am assuming that as I move my triangle, it does not change its area. If I have a triangle, a right triangle, What is the area of a right triangle of sides A and B? Area of a triangle of sides A and B, yes. 1/2 AB. How do we prove that? So if you go back and if you say, if I have a rectangle of size x and y, I'm going to define its area to be x times y. Then in that case, if I draw a diagonal and I'll have two right triangles, these will be basically reflections of each other. Or you can rotate one into the other, or you can flip one into the other. And so each one of them should be half. So it's always, what am I assuming? I'm assuming I know the area of a rectangle is x times y. So if it's a triangle, if it's a right triangle, it's going to be 1/2 that. What's this angle over here? So what would this angle be right here? 90 degrees. So if this is theta over here, this would be 90 minus theta. If this is theta, this is theta, this is theta, and this is theta. It has to add up to 180, so this has to be 90 degrees here. And by similar arguments, you get all of these are right angles. So we have a square of length A plus B, and we have 4 triangles, and then we have a smaller square of length C. Okay? Let's calculate the area of the big square 2 different ways. What's one way to calculate the area of the big square? A plus B squared. So one way is A plus B squared. What's another way to calculate its area? So one is C squared, but that's not the whole thing. What else do I need? The areas of the 4 triangles. So it would be plus 4 times 1/2 AB. So if you expand this out, you get A squared plus 2AB plus B squared is C squared plus 2AB. All right, the 2AB's cancel, and you get A squared plus B squared is C squared. And so we often put in a shaded box to mean QED, that which was to be proved, quod erat demonstratum, the proof is over. So this is the proof of the Pythagorean theorem. This is one of the most important results in multivariable calculus because we're going to use this to calculate distance between objects. If I want to know what's the distance between these 2 points, this is the straight line distance. Are you always able to do the straight line distance? Theoretically, you could always say, well, I can just do this. So where's the situation where you might not be able to do straight line distance? Where you want to get from point A to point B, but you can't just walk directly. So what might be 3 dimensions? I may not be able to just walk up. But let's say 2-dimensionally. Can you imagine a situation where you can't just walk? More basic than that. There's something in the path. I'm a Bostonian. For the most part, I hate New York City. But one part of New York City is well done relative to Boston. Any thoughts? The grid system in Manhattan. The grid system in Manhattan is terrific. You know, you've got your north, south, your east, west. But you can't just go diagonally through buildings sometimes. And in fact, there was an interesting court case, I think, years ago. I think this is true, but it could be a joke, where someone was caught selling drugs within a school, and the penalty is higher if you're within a certain distance. And they were within a certain distance according to Pythagoras, but because of the way the city blocks were, they were just a little bit over. And there was an argument as to whether or not they should be subject to the harsher penalty for being too close to the school. Probably a joke, but you know, I don't really want to check because I enjoy just the thought of the court deciding whether or not the Pythagorean theorem applies here. All right, everybody happy with this proof? I want to show you another proof of the Pythagorean theorem that really highlights what's going on. All right. So it's called dimensional analysis. How How many of you have seen dimensional analysis in maybe like a chemistry class or a physics class? Sometimes they do factor labeling. It's really useful to put in units and keep track of what's going on. So I'll give you a great example. So imagine you have a pendulum, and the pendulum is swinging under gravity. And we want to calculate the period, how long it takes to go back and forth. And so we'll start off initially at some angle. The pendulum has some length L. There's the force of gravity G going down. And we have the mass of the pendulum. So the period T is in seconds. Let's look at the units we have. We have the angle theta, which is unitless. We have the length of the rod, and that's going to be in meters. We have the mass, m, which is in kilograms. And then we have g, the acceleration due to gravity, which, anybody remember the units of acceleration? Meters per second squared. So we need to somehow use these four objects to get a unit of seconds. Who's the odd one out? Which one cannot be involved in the final answer? Mass. There's nothing that can cancel the units of mass. So without doing any work, we would predict that the period should be independent of the mass. How can I combine these well, the theta can come in however it wants. How can I combine length and gravity to get seconds? So what's the only way I can combine them? How would I combine length and gravity to get seconds? Yes?
L over G.
So if I do L over G, that'll be meters divided by meters per second squared. That'll be seconds squared, so you're close. So how do I have to modify this? Take the square root of this, and now it can have any dependence it wants on theta. So I'll say times some function of theta. It turns out that function of theta is, I think, 2 pi. But there's no way to see that from units. But look, before we do any experiments, we already have a sense of what the answer should be. It should depend on the square root of L over G. So if I quadruple the length, the period should double. This is the power of dimensional analysis. It gives you some idea of what the formula should look like. Okay? Are people ready now to see the Pythagoras? So I'm going to prove the Pythagorean theorem with dimensional analysis. Okay? So we have a right triangle, A, B, C. And I want to calculate the area. I'm going to call the angle down here theta. And I claim the area as a function of the theta and hypotenuse has to be of the following functional form: f of theta times c squared. So let's think, what I'm saying is, if I double the hypotenuse, the area goes up by a factor of 4. If I triple the hypotenuse, the area goes up by a factor of 9. So we'll see now if you use the same language I used when I took geometry decades ago. CP, CTC, corresponding parts of congruent triangles are congruent. Does it sound vaguely familiar? If you think about what happens, if I increase the C by a factor of 2, I'm going to double B and I'm going to double A. And the area is just 1/2 A times B. So if A and B go up by 2 each, then the area goes up by a factor of 4. Conversely, if I rescale this by a factor of 3, these each go up by 3, it should go up by a factor of 9. So do you agree that functionally the area should depend on the hypotenuse squared? And then I have no idea how it depends on the angle. But making progress. Okay? How many of you remember your geometry classes? All right. All difficult proofs in geometry seem to boil down to one thing: drawing at least one auxiliary line in a very clever way that then makes the problem obvious. And the challenge is figuring out where to draw the line. So there's a great method of proof called divine inspiration. So we're trying to deal with right triangles. Can you think of any line we could draw that might give us more right triangles? I'm sorry? Excellent. So we go from the right angle to the hypotenuse. And so before I forget, throughout the semester, if you make comments in class, please email me. I like to keep track in my book as to who's making comments. If it's a bad comment, don't email me. I will always forget bad comments. But this way, when I write letters of recommendation, I can be specific. And sometimes you might think this is not a difficult thing, but a lot of times it turns out it is. The other thing is I want to build you up to be confident to speak in public. When I was an undergraduate, I was very afraid to speak in public, and there were lots of times I knew the answer and I could have impressed the professor and just could not. I want you to get comfortable speaking in public. So even if the question seems easy, please volunteer. So if we draw the right angle, the altitude like this, we've created two more triangles. I will give them the very boring names of triangle 1 and triangle 2. What is this little angle over here? This angle down here. Well, if this is theta, what's the angle up here? 90 minus theta is here. So we have three similar triangles. We've just said that the area of a triangle is f of theta times c squared. The area of triangle 1, so area of 1 plus area of 2 equals area of the whole. What's the area of triangle 1? A squared times f of theta. Why? Because A is the hypotenuse for triangle 1. So this is f of theta times a squared. What's the area of triangle 2? F of theta times b squared. And what's the area? Well, we already know that it's f of theta times c squared. All right, what should we do? So we have to justify. If f of theta is 0, we can't divide by 0. Is f of theta 0? No. If f of theta was 0, then the area of the triangle would be 0. So since f of theta does not equal 0, you get a squared plus b squared is c squared. And there's a dimensional analysis proof of the Pythagorean theorem. And it gives you some idea of where it's coming from. It's coming from areas. We had to be a little bit careful with division. It's not that bad, but you do have to say that f of theta is not 0. Out of curiosity, how comfortable are people with elementary arithmetic like division? So if I give you like 16 over 64, 1/4, 19 over 95. Yeah, amazingly, it's the algebra that hits people the most in calculus. 49 over 98, 1/2. We'll do one more. 12 over 24. I'm sorry? 1/4, right? No, 12 over 24 is 1/2. Right? No, you're confusing me. It's 1/4. No, don't confuse me. It's 1/4. All right, crap. I really wish this wasn't being recorded now. All right, 16 over 64, cancel the 6's, get 1/4, yes. 19 over 95, cancel the 9's, get 1/5, yes. 49 over 98, cancel the 9's, get 4/8, which reduces to 1/2. So obviously, 12 over 24, cancel the 2's, and you get 1/4, right? This is an attempted proof by example. This is not a valid method of proof. Just because something works for a while does not mean it's going to continue to work. There is only one way to prove by example. It's called proof by exhaustion. And the phrase should tell you that this is, in general, not an idea you want to pursue. You look at every possible case. And if you show it holds in every possible case, then you're done. If things are sufficiently small, you can roll up your sleeves and you can do every possible case. But in general, just because it works for a couple of cases does not mean it will continue to work. So I do a lot of work in baseball mathematics. I actually have several students working with me right now on a multi-million-dollar MLB court case. This is not the first time I've had students do stuff like this. Out of curiosity, how many people follow sabermetrics, baseball mathematics, stuff like that, or sports analytics? Okay, so there's a lot of really good mathematics and statistics that's going on here. You're trying to find out which statistics really matter, which formulas give you a good sense of predicting. So one of the extra credit problems is a way to try to predict the probability that one team beats another. And it involves looking at just two pieces of information, the two teams' relative winning percentages. So, and then we'll end with this. So A wins P% of the time, B wins Q%. So I'm going to write down 4 formulas. I think it's, yes. So actually I could double check the notes. I believe it was, these were, yes. So there were 4 possible do I want to write it like that, or do I want to just do? All right, so these two signs are the same. So there's 4 choices. I can choose the plus sign here, and the plus sign here, the plus sign here, the minus sign here, the minus sign here, the plus sign here, the minus sign here, and the minus sign here. There are 4 possibilities. One of these 4 possibilities actually does a really good job of predicting the probability that team A beats team B. And so as an extra credit homework problem, try to figure out which of the 4 does a good job. So I'll give you a hint. You want to try to consider special cases. And if anybody wants to say a special case right now, we can end with that special case. What would be one special case that you'd like to check? Okay, in what sense? Okay, so if P equals Q, what should you get?
1/2.
You should get 1/2. So P equals Q, you should get 1/2. That's a great check. Any football fans here? Anybody know a good team that might be useful to use for this from last year?
Browns?
The Browns. Why might the Cleveland Browns be a good team?
They won 0 games.
They won 0 games last year. Is there anybody here who is a Cleveland Browns fan?
Rough life.
I mean, you've got 4 wins in the last 3 years.
I know. It's not getting any better.
No. But you can't get much worse.
It's true. Only one
So for the Cleveland Browns, they won no games. What do you think should be the prediction if somebody plays the Cleveland Browns?
100.
Yeah, so long as they're not the Cleveland Browns themselves, they should. So try to think of special cases and use that to get a sense of what's going on. Okay, so I think this is a good place to stop. The videos will be posted hopefully later today.